The next speaker. Casassus. Am I correct? Casassus. I'm sorry. Please.
So I'm Simon Casassus here from University of Chile, and I'd like to thank the organizers for a very interesting conference. I'm learning a lot about a phenomenon I didn't know much about. Microphone? Sorry. Okay. Today I'd like to share two phenomena which I find very interesting. The first one is about warps, and if I have time, I'll try to present another on another topic. So we've heard about warps already, and I'll try to go straight to the point. Antonio and Stefano already showed images about those shadows in transition disks, so meaning disk where we can see a central cavity. I think that there is a question about the shadowed material. I mean, if you have shadowed material, you expect the shadowed material to cool down. And so we should be able to measure the temperature drops. It turns out it's not always the case. So I'll start by summarizing very quickly the prototypical case of the 1425-27 warp, where we have this transition disk. So it's a ring surrounding a central inner disk. And, you know, those shadows along the outer ring can be interpreted in terms of the orientation of the inner disk. So the gas kinematics are consistent with the geometry of the system. So these are the observations here. And this is our model that includes the inflow of gas onto the inner disk. So this is radius, and this is the radial velocity. So you have infalling material that produces this twisted shape here, along with the change of orientation. So this is like a complicated picture, just to say that the warp must connect very fast from one plane to the other. It's comparable to the Keplerian rotation speed. But okay, so the kinematics are consistent with the warp. And when you look at the multi-frequency continuum with ALMA, so if you go from low frequency to high frequency, I think this is 130 to 700 gigahertz, you can see this decrement here that starts to fade at low frequency. That corresponds to a decrement in brightness temperature when you do a simple gray body model. Okay, so this point here coincides with the shadows, and in this system, then we see a drop in the temperature of the dust under the shadow. So this is all good. It's all consistent. And so we've heard about forcing of this inner disk by a companion, and this case is important because we know the companion in this system. It's a low-mass T-Tauri star, like TW Hydra orbiting a Herbig star. And if you do hydro simulations, you can actually reproduce the inner disk, and also you can also reproduce the infalling material, the fast infall. Okay, so it seems like everything is settled for HD 1425-27, but there are a few more other examples with rather puzzling properties. So in this case, HD 105-453, so we have very well-defined shadows here, but there's no clear decrement in the continuum. So this is the radio continuum. There's no obvious counterpart in the continuum. That's another example in Dewar 44, where we have these two-sided shadows. And in this case, there seems to be a drop in the continuum. In this case, there would be a match between the optical infrared shadows and the continuum. So I'll skip on this because I'd like to go straight to the point. Now, this is another interesting warp, JS 1604. where we have two-sided shadows, and to make a long story short, the kinematics are consistent with the warp. But I think that this summary of multi-epoch monitoring of the system is very interesting in connection with the previous talk also, because we see variability of these two-sided shadows. So these are all different epochs. So these are a polar expansion with radius and azimuth vertically. And you can see well, this is a two-sided shadow, okay, but it seems to wobble a little bit. A bit like in the model we just seen about the quasi-stationary shadows. Okay, so in this system, the kinematics are consistent with the warp as well. And this is yet another example of a warp where the ALMA image here in gray, in color scale, does not show any decrement in the position of the shadows seen in the scattered light. So these would be shadows, but we do not see any counterpart in the continuum. So in summary, from the observations, we have some systems that, some shadowed systems that have a continuum drop and others do not. So I think that this is puzzling. Why do we not see the temperature drop in some shadowed systems? Okay. So I'd like to propose an interpretation for this based on a simple model which tries to approximate the cooling of the material as it flows under the shadows. So material enters the shadows in Keplerian rotation, and it starts to cool, and then when it emerges, it heats up again, okay? So this should lead to a small shift in the minimum in dust temperature compared to the centroid of the illumination pattern. So these are all the equations I'll show. It's a very simple model that includes cooling from the surface of the disk. This is the forcing term, this is a heating term with this illumination temperature, which follows the illumination pattern, okay? And this is a key term. Oops, that's bad news. Okay. So this is a key term that corresponds to heating due to the transport of radiation from the rest of the disk. So you have to bear in mind that the disk shines in its own thermal radiation and heats up the material under the shadows, okay? And this last term here is due to advection of internal energy under the shadows. So when you put this all together, you get a very simple differential equation that you can solve. And the three parameters of this equation are the disk surface density, so this is the mass of the outer disk, the gas-to-dust mass ratio, meaning the dust properties in general, the dust filling factor and the maximum grain size. So the maximum grain size and the dust filling factor are super important to control the Rosseland opacity. And here is a summary of the values that you can get from different dust populations. So without going into details, it varies by a factor of 10 as a function of the maximum grain size. So the choice of the illumination pattern is crucial. Just to make a long story short, we adopted this illumination pattern here. So basically it's a square pattern that follows the illumination pattern from the shadowing due to the tilted inner disk. Okay, so this is the mean radiation intensity as a function of azimuth. And this is what we use to basically estimate the forcing term in the equation. And these are the solutions. So when you have a very massive disk, it's optically thick and smoothing by radiation from the disk. The rest of the disk is not so important. And you have the green curve. So this would be the massive disk case. Material flows into the shadow and its temperature would drop under the shadow and it starts to heat up again, and it heats up again when it emerges from the shadows. And if you go to a lower mass disk, all the purple curves here correspond to a lower mass disk with different grain populations. And I'd like you to pay attention to this other curve here. so the dash purple curve. That corresponds to a low mass disk and with a maximum grain size of 1 centimeter. So this would be optically thin to its own radiation. And the radiation from the rest of the disk smooths out any temperature drop under the shadows. So this is the model that I propose for this discrepancy, that some systems show a drop in temperature and others do not. Okay, so and I think it boils down to the outer disk being low mass and optically thin to their own thermal radiation. Also for HD 142527, so we predict a massive disk, and this is the very qualitatively we see the PA of the illumination pattern, and I've overlaid here the PA of the illumination pattern on the C18O integrated intensity. So this would be a molecular line tracer of mid-plane conditions. And we see a small shift in the position of the minimum in intensity relative to the PA of the scattered light. So it looks like I need to work on this more, but it seems that the shift is observed here. So I'll skip on the modeling for this other source, just to summarize on this question about why do some systems show a temperature drop under the shadows and why others do not. So basically it boils down to, according to a simple model, to the optical depth of the outer disk. So still have work to do here. There's a question on moving shadows and how would they impact on this simple interpretation. And of course, do a proper radiative transfer model using that includes advection. So I don't know how much time I have left. Sorry? How much time do I have left? A lot of time? Okay. 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 So I'll try to quickly talk about another topic, which is about an FURE object that many of you may be familiar with because it's the brightest of FURE objects in total luminosity. And so this is work in collaboration with Lucas Ciesa, Sebastian Pérez, and Antonio Alves, who are here in the room also. In 2016, we reported on this ALMA image of VA3 Ori, where we had this structure with a bright core and a faint halo. And when we estimated the spectral index, we found that the central core was, this region here was optically thick, okay? So this allowed us to measure the temperature, and we found that this break here corresponded to the temperature of the condensation of water. So I thought this was interesting, and we published this as a letter. So now I'll compare with multi-frequency observations. So this is 90 gigahertz and 355 gigahertz observations. Maybe I'll be repeating myself here a little bit, but the idea here is that we have an outburst of an FURE outburst that pushes the snow line outwards, and the core here is optically thick, so grains do not grow, they cannot coagulate, and we have very high dust optical depth, which corresponds to this optically thick spectral index alpha in specific intensity. Okay, so this seems consistent. And what was really puzzling and what I would like to share with you today, I'm not sure about the interpretation yet, is the spectral index across bands. When I compare 90 gigahertz with 230 gigahertz and 230 gigahertz with the higher frequencies. So this is the spectral index, and pay attention to this one here. The spectral index in the core goes down to 0.9, so that's below 2. The continuum is optically thick, and yet we have a resolved image here of a spectral index that goes below 2, so order 1. So cuts, radial cuts of this spectral index, where we see spectral index between 90 gigahertz and 230 gigahertz going down to 2.5 in the center. Within band 6, within these two close frequencies, we are able to measure the spectral index I've just mentioned. It's around 2. But if you go to the spectral index between band 6 and band 7, it goes below 2. So this is really puzzling. You can cast this spectral index in terms of the brightness temperature. So if you compare the brightness temperature at low frequencies in band 3 is 90 gigahertz. This is band 3. The black is band 6, and we see the band 6 here too, compared again to the band 7. So these two graphs have been smoothed to the same angular resolution. They're directly comparable. And basically what happens here is that the band 7 brightness temperature is lower than the band 6 brightness temperature. Okay? So when you go to lower frequencies, you do not see this effect. And we think that this is due to the band 3 being mildly optically thin. So basically, we interpret this in terms of a temperature inversion, saying that the midplane of this accreting disk is hotter than the surface. For us, it's a temperature inversion because normally we think of the surface being hotter than the midplane on a passive disk. Okay. This is a radiative transfer model for the concept. So we are including viscous heating in the midplane that shapes this. So this is the vertical axis. Above the midplane, this is radius, and this is the location of the 150 Kelvin line. So the condensation of water. And this is without viscous heating. So you see that the inclusion of viscous heating pushes the snow line further out compared to just the passive disk case. The main free parameter in the model is the mass accretion rate. So basically we parameterize the viscous heating in terms of the mass accretion rate. So the ejection of energy is directly proportional to this accretion rate. And these are the observations. So basically these are the observations. This is the model with viscous heating and without viscous heating. Seems to have a fairly good match to the data. And the red curve here is our model. So just to finish, I'll show this sketch that summarizes these observations in VA3 ORI. So the midplane would be heated by viscous dissipation. When we observe at high frequencies in band 7, the unit opacity surface is higher up, and so that's why it's cooler compared to when we observe at lower frequencies, where you go deeper into the disk and sample hotter regions. So that's all. Thank you.
No.
Okay. I just want to understand. Sorry. In standard models of T-Tauri stars, the region where you have that the viscous heating in the midplane is higher than what you have, this inversion temperature is pretty small. What kind of mass accretion rate or do you need to get this kind of inversion over the region of that you need? Is there? Yes, I couldn't see it. Oh, okay, is there. So it goes very much up. Yeah. Okay. Have you any evidence that there has been that there is such a high accretion rate? Any other evidence?
No, sorry.
So that's a good consistency check. But remember, this is not the stellar accretion rate. This would be the mass injection at a given radius in the disk. So I'm not sure whether we can connect this directly with the mass accretion rate on the star end. But what is the stellar mass accretion rate in VA3 ORI? I don't remember. I think someone must have figured that out. I don't know if anyone in the audience knows about it.
Definitely not.
Okay.
But, sorry, ladies first.
Just to follow up this with this figure, so I'm really puzzled to have this kind of curve, the accuracy rate, as a function of the radius, because if this is not constant, that would mean that certain parts of the disk would be depleted, other parts you have an accumulation of material. And we know that this object has been in outburst for more than 100 years, since the 19th century. So this cannot be a steady state disk. So how, can you comment on that?
I completely agree with this. Sorry. So thanks for the question. I completely agree. This is very puzzling. And of course, this cannot be a steady state situation. And indeed, as you said, the source is a burster, right? So it's not going to burst.
Sorry, you modeled the disk in the frame of Shakura-Sunaev thin disk.
Yes. No, a thin disk.
Thin disk approximation.
No. This is a thick disk. It's a flare disk, yes, with a scale height.
Flare disk, but equations which you used, hydrodynamical equations.
No, this is only a parametric disk, so that we fed into a radiative transfer code, including viscous heating in the midplane.
It's clear. But, sorry.
Viscous heating based on the Shakura-Sunaev information. Yeah. That's probably the answer. Just a continuation to the concern raised by Agnieszka. So it's accretion rate 10 to the minus 4 at distances of about 80 astronomical units. So even if it's not a steady state, it cannot be a steady state, because otherwise it will be depleted within thousands of years. The entire disk will be gone. But even if we assume this is triggered by an MRI burst, an MRI burst doesn't go any further than several AU from the star. So it cannot propagate up to 80 astronomical units. I have never seen it in any simulations. So what, even if it's a burst, and it looks like the entire disk or a large fraction of the disk is involved into a burst, that's a big enigma for me.
So this is all very enigmatic to me too, I must say. I'm not an expert. I'm just starting to get puzzled also about these objects. But maybe, we could have made a mistake. I never know. But we parameterized the viscous heating proportionally to this mass accretion rate times the angular rotation pattern to some power, I think is cube. And that's it. We didn't add anything else. But this is a local accretion rate. So it's depleted, but there's an envelope also, remember. In this system, it's a big envelope. But you're right, I should figure out what's the time scale for the depletion of this inner region of the disk. I agree with you that this cannot hold very long, I suppose. Yeah.
Wait.
So I wonder whether you can have another effect playing a role. So if you, for simple model, we have a single grain population and your wavelength is close to the, basically to the resonance. So you can have a band in the opacity that can actually mimic that. So I wonder whether in this particular disk, you have a peculiar distribution of grays such that you can invert the spectral index close to the opacity, right? Because it grows and then it goes back down towards the Rayleigh-Jeans limit. But you have some point where the spectral index actually inverts. So that can be also a simple explanation. So that's one comment. Another one, on earlier, where you showed the shadows. So I think that for the sharp shadows, I agree that it's very interesting, all the thermal time scale problem you're studying. But I wonder for the less sharp shadows, like, like half of the disk being in shadow. So half of the disk is illuminated, right? Only like the bottom part that you don't see, it has to be illuminated. It's just the top part, for example, that you don't see. So half of the energy is going to be propagated into the disk midplane. So the expected difference in temperature is 4th root of 2. So that's very difficult to see in dust continuum. That's my guess.
Okay, thanks. About the first question on the dust population or the comment, I agree that we should expect differences in grain population, but I do not see how that could explain the temperature inversion and how you could get a hotter meat plane like that.
I just mean it's a brightness temperature inversion, but there is no temperature inversion.
Okay, I'll need to talk about it
You
more.
will discuss this later, 2 by 2, if I mean.